Hello, my name is Ulrike Dydak. I'm professor at Purdue University and I have the pleasure to give the introductory presentation to the session Basics of MR Spectroscopy. My talk is entitled Basic Principles of MRS, Chemical Shift, J-coupling, Relaxation and Field Strength Effects. I am disclosing that I'm consulting for a clinical study with American Regent. For this lecture, I will assume that you all have some basic knowledge of the principles of MRI and how signal is generated in MRI. While MRI uses the signal from water mainly and from fat molecules and provides us with anatomical and functional images, MR spectroscopy offers to study the signal from protons and other nuclei giving an MR signal bound to many other molecules. It thus offers to study biochemistry in vivo. Here you can see two examples, a proton spectrum from the human brain, as well as a phosphorus spectrum from the human liver. Each of these peaks gives us information about specific metabolites and neurochemicals that play important roles in physiological and pathophysiological pathways and are therefore of interest for diagnostic or research purposes. Now, how do we obtain such a spectrum? First of all, MR spectroscopy and MRI share exactly the same physical principles. And by that I mean excitation, refocusing, relaxation mechanisms, spin echoes, all of these concepts are identical as in MRI. In fact, the first MR signals were spectral signals long before we added spatial resolution to make beautiful images. In imaging, the signal of hydrogen nuclei in water molecules is measured mostly because of its very high natural abundance. In spectroscopy, we're interested in acquiring signal of protons in molecules other than water and to use this method to convey the chemical composition of the tissue of interest. Now, information on and information and identification of these molecules is based on difference in the resonance frequency of different tissue metabolites. This difference is also called chemical shift. To understand the basis of the chemical shift, let us quickly review the Lamarck frequency. The Lamarck frequency is given by the gyromagnetic ratio gamma and the external magnetic field B0. For example, for hydrogen nuclei, that is protons, the gyromagnetic ratio is about 42 MHz per Tesla. And thus our 3 Tesla MRI scanners operate at about 128 MHz. A 7 Tesla scanner will operate at 298 MHz. Not only hydrogen nuclei give rise to MR detectable signal, there are many more. The main criteria is that the spin is non-zero and enough sensitivity to detect them in vivo. But typical examples you will find in the literature will include phosphorus 31, carbon 13, sodium 23. Each of these nuclei has a different gamma and thus will resonate at very different Lamarck frequencies, requiring their own hardware for transmitting and receiving. But in this lecture, I will solely focus on proton MRS. The most basic MRS sequence is a simple pulse acquire sequence. It consists of a 90-degree excitation pulse and the acquisition of the resulting free induction decay signal, or FID signal. In MRI, we would only acquire the very first point of this FID signal and move on. However, in spectroscopy, we must acquire as much of this FID signal as reasonable. More precisely, the time of sampling directly translates in the spectral resolution that we can obtain. For example, if we needed to get a 1 Hz resolution, we would need to sample the FID for 1 second. For a 2 Hz resolution, we need at least 500 milliseconds. And for a 5 Hz resolution, we need to sample for 200 milliseconds. In MRI, we are only interested in the total signal, not the spectral resolution. That's why only acquiring the first point of the FID is sufficient. Note that this sequence, as shown here, has no gradients played out, and thus does not contain any localization of the signal, nor any of the other typical components of an MRS sequence, such as water suppression or outer volume suppression. Okay, so after sampling the FID, which is a sinusoidal signal that decays exponentially according to the relaxation properties of the metabolites, we will apply a Fourier transform. Thus, we are changing from a time axis to a frequency axis that will show a peak at the frequency of this FID signal. Typically, it will look like this one here. the water signal centered at the Lammers frequency. However, if we look more closely, this FID signal here was a mixture of many different resonance frequencies, and we will find more but much smaller peaks to the right of this water peak. A typical proton spectrum. Please note that water concentration is about 10,000 times higher than the millimolar concentrations of the metabolites we are interested in. Therefore, very often we will use water suppression strategies in our MRS sequence. Now, all of these peaks in this spectrum still stem from hydrogen nuclei, but I had just told you that the resonance frequency only depends on the gyromagnetic ratio and the field strength. The gyromagnetic ratio is the same for all of these peaks, so how is this possible? Well, there is not only the nucleus in the atom, we also have electrons around it. The electron density in an atom can be considered to cause small currents that generate a magnetic field that opposes the B naught that is caused by the scanner. So we have this small magnetic field due to the electron clouds. This process diminishes the local field from the scanner, and therefore we also sometimes say that the proton is said to be shielded. The electron density of hydrogen in larger molecules depends on the electronegativity of nearby atoms, such that the exact Lammers frequency becomes very sensitive to the chemical environment. Let's consider these three molecules here, all with hydrogen atoms that will provide signal. Water on the left, N-acetyl aspartate, a neuronal marker and the biggest peak in a healthy brain spectrum in the middle, and lipid. Each of these proton groups has a different chemical environment, giving rise to a different shielding of the B naught field, and thus to a slightly shifted resonance frequency. We call this specific shift in resonance frequency the chemical shift. More precisely, electronegative oxygen atoms in water will shift the electron density away from the protons, leading to reduced electronic shielding. In fact, we usually consider water signal to be the closest example to the signal from free hydrogen nuclei. However, in this methyl group of NAA in the middle here, the bonding is different, and the next oxygen atom is further away. Thus, there is more shielding than in water, reducing the resonance frequency somewhat for the methyl peak of NAA. Finally, in this lipid example, no electronegative atoms are anywhere nearby, and thus the hydrogen nuclei are shielded the strongest. Therefore, the lipid peak will be at yet a lower frequency, as seen in this spectrum here. The chemical shift in Hertz is proportional to the magnetic field strength. Thus, if measured in Hertz, the difference between this NAA peak here and the water peak is 177 Hertz at 1.5 Tesla, but double that, 354 Hertz at 3 Tesla, and yet another number at 4 Tesla or 7 Tesla. In order to normalize the frequency axis across field strengths, and thus across scanners, the frequency unit is usually expressed in ppm, which stands for parts per million. It is calculated as the difference to a reference standard in Hertz, divided by the reference standard. Since chemical shift is in Hertz, but the resonance frequencies of hydrogen, or the reference frequency here, will be in megahertz, we then multiply by 10 to the 6 to get values in the single digit and to get a value that stands for parts per million. Note that water is not the typical reference standard for proton MRS, but for historical reasons, it was TMS, which has the lowest precession frequency compared to most metabolites in proton spectra, but is only used in NMR. So for in vivo spectra, this just means that NAA will always resonate at 2.02 ppm. You can just remember at 2 ppm, and water at about 4.7 ppm. Now, important as a take-home message, the chemical shift expressed in ppm will be independent of the magnetic field strength. That means NAA will always be at 2 ppm. If we wanted to calculate the value of 1 ppm in Hertz, that will be different at different field strengths or the different nuclei. So here I give you some examples. At 1.5 Tesla for protons, 1 ppm equals 64 Hertz. At 3 Tesla it would be 128, at 7 Tesla it would be 298. And for other nuclei these numbers will vary again. As we just saw, increasing the magnetic field strength will also proportionally increase the chemical shift of the peaks on a Hertz axis, thus requiring us to sample a broader bandwidth in Hertz. Remember that the bandwidth that you sample will be given in Hertz as a parameter on the scanner. In this example, you see two brain spectra acquired in the same volunteer and same brain region, but at two different field strengths, plotted on a Hertz axis, so you can appreciate the increased spectral bandwidth that the spectrum spans at 3 Tesla. Now in this example, the same two spectra are plotted on the ppm axis. Again, on the left at 1.5 Tesla, and then at a higher field strength on the right side. And you will appreciate the increased spectral separation at the higher field strengths, yet we have a normalized x-axis, so NAA will sit at 2 ppm on both spectra, creatine sits at 3 ppm and at 3.9 ppm at both spectra, and choline at 3.2 ppm. In fact, since most of metabolites have several hydrogen nuclei that give rise to MR signal, each metabolite has its very own spectral signature, also sometimes called a basis spectrum. An in vivo spectrum is basically the sum of all of these spectral signatures, weighted by their concentration in the tissue sample. Note how some peaks have a clean singlet structure, as seen here for the two creatine peaks on the fourth row from the top, whereas others, as in glutamate or inositol, show more messy multiplex structures. Let's take a look at what causes this difference. The line splitting is due to the influence of neighboring nuclei, or the J-coupling between neighboring nuclei. Now let's assume you are a hydrogen nucleus, and the person next to you is another hydrogen nucleus. Now that hydrogen nucleus next to you might have its spin up or it might have its spin down, and the probability of that is equally high. Therefore, because you're coupled to that other nucleus, they're close enough, you feel its influence, your signal will split into a doublet with two peaks that are equally high. If you now have two neighboring nuclei that are close enough so that you feel their influence, so that you're coupled to them, then their spins can both look up or both down, or one looks up, the other down, and vice versa. So your signal will split into a triplet with a ratio of 1 to 2 to 1. If you have three nuclei, then the situation gets more complex, as you can see in this example over here, with 3 times up or 3 times down and all the combinations in between, giving rise to a quadruplet in this case, and so on. Let's take a look at the molecule lactate that has this methyl group here, the CH3 group here with the green circle, that gives a signal, as well as the CH group with the red circle that gives another signal. Now these two have different chemical environments and therefore will resonate at two different chemical shifts, namely at 1.3 ppm and at 4.1 ppm. Let's take a look more closely. So here, this is a cartoon, and I have depicted the same lactate molecule here in a more simple way, where we concentrate just on the CH and the CH3 group. Again, since they're in different chemical environments, they will resonate at different chemical shifts, namely at 1.3 and at 4.1 ppm. The CH3 group, the signal from the CH3 group, will be 3 times as large because there's 3 hydrogens that give rise to this signal. They're all completely equivalent, therefore they give rise to one signal here. Now, however, this CH3 group is influenced by the CH group, and this proton here in the CH group can either look up or down. Thus, our signal for the methyl group will go into a doublet. That's the very well-known doublet structure of the lactate at 1.3 ppm. Now, of course, vice versa, there's also influence. The CH3, the 3 protons from the CH3 group, will have influence on the signal from the CH group. Now, here the situation, of course, is more complex, and thus we end up getting a quadruplet. As you can see in this last slide to this example, this is now measured in a phantom, a lactate phantom, and you will appreciate that the signature looks exactly the same as in my cartoon, with a doublet at 1.3 ppm and a quadruplet at 4.1 ppm due to the weak coupling between these moieties. Well, all of this together gives rise to about 16 different metabolites that we can detect in the human brain. I'm just depicting a few here. So the biggest peak is usually in a healthy brain is NAA, which is a neuronal marker, or N-acetyl aspartate. Then we have creatine, total creatine, which stands for creatine and phosphocreatine and acts as an energy buffer. We have choline containing compounds that is in membrane synthesis and degradation, and therefore plays a big role in cancer. We have lactate, which is typically not seen in the healthy brain, but is an end product of anaerobic glycolysis and therefore often elevated in a lot of pathophysiologies. Then glutamate and glutamine that are so strongly overlapped that at 1.5 Tesla and 3 Tesla actually also, it is very hard to really quantify them separately. Only at higher field strengths they separate enough. Then we have the neurotransmitter GABA that is sitting underneath all of these and needs usually some special editing techniques to get quantified. As well as the antioxidant glutathione, same situation. It's a very small peak that sits underneath here of the creatine peak and usually needs editing methods to get quantified at 3 Tesla unless you go to very high field strengths like 7 Tesla. And then myoinositol, which has its peak over here, and is an osmolyte and glial cell marker. These are just a couple examples. And then once in a while, of course, it can also happen that you scan your colleague, graduate student, and there is some strange peak in the spectrum, in the brain spectrum that you've never seen before, and you wonder what that is. And that is a wonderful example, though a very old one, as you can see from that very old scanner surface. That yes, you can also see exogenous molecules in the brain. You might already have an idea what this is. This is indeed the peak of ethanol. So this person had been drinking quite a bit the night before. Now let's go back to the very basic MRS experiment. Remember, we are sampling our FID, and each frequency that is within the FID will give rise to a peak. The resonance frequency determines the position on the spectral axis of this peak. Also, the amplitude of this very first point of the FID corresponds to the area under the peak. And this area under the peak is exactly the quantity that we are after. It represents the concentration of the metabolite. So when we do an MRS study, that's usually what we want to measure. Is a concentration different in a particular patient group, or has it changed after a certain treatment? Let's look at some other relationships as well that have to do with relaxation mechanisms. As you can see here, the faster an FID decays, the lower and broader will be the peak. Therefore, for spectroscopy, shimming and having a very homogeneous magnetic field is of utmost high importance. As you can see here, the rate of the decaying signal is given by the relaxation time T2 star, and that is directly reflected in the width of the peak on the frequency axis. Now, T2 relaxation in general, and T2 star relaxation as well, is caused by the dephasing of the spins in our transverse axis. As we know, the T2 is stemming from microscopic inhomogeneities and spin-spin interactions, whereas T2 star comes from macroscopic inhomogeneities and spin-lattice interactions. And T2 star usually is much shorter, and therefore the signal decays very quickly. Therefore, most of our MRS experiments are spin echo experiments that make use of a spin echo in order to regain the signal of the spins at a later time, so that we can have time to put in localization schemes and other type of sequence elements that are needed for a MRS exam. Now this slide here shows you the influence of the choice of echo time on a spectrum. You have 3 spectra here that are all acquired in the same subject in the same brain region, but just at different echo times. A short echo time of 30 milliseconds, a longer echo time of 144 milliseconds, and a very long echo time of 288 milliseconds. You will appreciate the T2 star decay of all of the metabolites. And take a look at the ratio of choline to creatine. It is different in all 3 echo times. So that signifies that the T2 star of each metabolite is different. For example, T2 of choline in gray matter at 3 Tesla is 207 milliseconds, whereas of creatine in gray matter at 3 Tesla is 156 milliseconds. In fact, you also should note that the T2 will vary across different tissue, for example, gray matter and white matter. It can vary with age, and it definitely is different for each metabolite. And it is influenced, so the appearance of your spectrum will be influenced by the echo time. Unless you're acquiring an FID where there is no echo time, then there is no influence of echo time. You always have to bear that in mind and never compare spectra across different TEs. The T1 relaxation time will influence your choice of TR. As you know, the TR is the time between 2 excitations and also the time that we need for the magnetization to go back into longitudinal direction. Typical T1s of metabolites are 1 second and longer. So if you wanted to have a fully relaxed spectrum and you wanted to use 5 T1s in between 2 excitations, but you still need some 128 averages, that becomes very quickly a long scan. So therefore, we usually like to take a compromise, but we have to accept that we have some saturation loss or loss in SNR to that compromise. Typical TRs used in proton spectroscopy range between 1 to 2 seconds. These 2 tables give you 2 examples for measured T1 and T2 at 1.5 and at 3 Tesla for the metabolites NAA, total creatine, and choline, so you can see in what range they are. These were measured in white matter. Altogether, remember that relaxation times differ for different field strengths. They differ for different metabolites, but they also differ for different brain regions. Finally, in the last 2 minutes, I want to talk about the influence of the magnetic field strengths once more. We have seen, first of all, as in MRI, that we get a higher SNR with higher field strengths. So in this cartoon, we have our 2 peaks and a coupled peak. And yes, if we were lucky, we would get a almost ×2 increase of SNR. Usually that's not completely the case, but let's say we go from 1.5 Tesla to 3 Tesla. That should give us a increase in SNR by a factor of 2. Now, the other bonus, the big bonus, is that increased spectral separation that also goes linearly with the field strengths. So remember, the chemical shift is linearly proportional, therefore our peaks will be separated by double the amount of space on a frequency axis in Hertz. Notice that J coupling is independent of the field strengths. It stays constant. This difference between these 2 doublet peaks will stay constant across field strengths. Now, other relaxation properties are that T1s usually get longer, T2s usually get shorter, and both of these contribute to our signal decreasing again somewhat. So we don't really get a full twofold increase in SNR. Furthermore, inhomogeneities, field inhomogeneities also increase with field strengths, and therefore our signal will reduce some more. The main benefit at higher field strengths is the increased spectral separation. Of course, also to some degree the higher SNR. And with the last 2 slides, I would like to show you some examples, and I'm using 2 slides that were generously given to me by Ivan Tkach from the University of Minnesota. Here's an example of myo-inositol and the signal at 1.5 Tesla, where you see here at 3.4 ppm the signal, and then you see the difference and how these complex structures here split up and become very nicely measurable if you measure it at 9.4 Tesla. The same thing is true for our measurement of glutamate and glutamine, which is often we want to only measure glutamate and not have it confounded by glutamine. At 1.5 Tesla, that's not possible because those two peaks are sitting basically exactly on top of each other. At 4.7 Tesla, you already start to see a separation, and if you have a very good quality spectrum, you might be able to quantify these different peaks sitting next to each other at this time. At 9.4 Tesla now, these are clearly separated, and you can very easily quantify glutamate alone and glutamine alone. Last but not least, this here is an example from a human brain spectrum acquired at 7 Tesla with a very short echo time of 6 milliseconds with a steam sequence. And you will appreciate how the increased spectral separation of all the different peaks, as well as the simplified coupling structure or simplified multiplet structure of some of these peaks, allow us to very nicely quantify different peaks, even like taurine and schiloinositol here. You even start to identify the GSH peak in the phosphocreatine underneath the phosphocreatine peak. Or you can nicely separate glutamate from glutamine. With this lecture, I hope that I have been able to convey the following take-home messages. MRS may be used to study the chemical composition of in vivo tissue. Different chemical environments of the protons give rise to shifts in resonance frequencies, which we call chemical shift. Each metabolite has its specific spectroscopic signature that contributes to in vivo spectra, which depend on magnetic field strengths and acquisition parameters. And that higher magnetic field strength provides increased SNR and increased spectral separation, thus facilitating better quantification of metabolites. And I want to thank you for your attention.